Hello, calculus students. This is going to be a lesson on a technique of integration called U-substitution. And it's important that you remember that what we're about to discuss is a technique of integration. It's not a rule. Derivatives have rules. If I hand you a trig function, you can take its derivative. If I hand you an exponential, you can take that derivative. If it's an exponential multiplied by a trig function, you can use the product rule with the other ones to take that derivative. They're all rules. When it gets to integrals, what you have to remember is life isn't fair and integrals don't make sense. Now, that's not really true. They do make sense eventually. But the point is, you can't figure out an antiderivative necessarily just by looking at it. You need to consider the fact that an antiderivative is a reverse derivative and make sure that you are following all the backwards rules of differentiation. All right. So before I even get into this technique, I want to talk about some general antiderivatives here. So if I had the antiderivative of, let's say, 3x to the fifth dx, we need to remember the backwards power rule, where I add 1 to the power and divide by the new power. And if it's an indefinite integral, I need a plus c. No problem. One of the other ones we've talked about is if I have the integral of like 4 over 3x minus 1 dx. That's come up before a little bit. And I had told you that the antiderivative of a constant over a linear is going to be the ln of the bottom divided by the derivative of the inside. So that'd be 4/3 ln absolute value of 3x minus 1. We've had other ones where if I had the integral of, let's say, sine 2x dx, I'd say, all right, well, what's the antiderivative of sine? That's going to be negative cosine. And in fact, the derivative of 2x is 2, so I need to divide by 2 as well. So I take the antiderivative of the trig and divide by the derivative of the inside. Okay? Technically, what we've been doing is we've kind of been doing some U-substitutions in our head. Okay? And so I'm going to push that a little bit further now and say, well, what if they're a little bit more complicated? All right. So there's this box up at the top if you're looking at your notes. That's just kind of like a text-based reminder of what I'm about to say in the video. But I'm just going to come down and explain it as I go. So the first type of U-substitution, I'm kind of giving them names. These are all my language here, but I'm going to call this a basic U-substitution. So the way a basic U-subs work is if you have a product or a quotient you can't get rid of. So I have 6x times 4x squared plus 3 to the 9th dx. Right now, the only way that you would have to take the antiderivative there would be to multiply that by 9 of itself. All right, so I'd have 9 4x squared plus 3, multiply them all through, then distribute the 6x, then use the backwards power rule. Yeah, no thank you. So instead of doing that, we're going to do a U-substitution. All right, the technique works this way. The thing that's in parentheses, you're going to call that U. So U is 4x squared plus 3. I do not include the exponent, just the inside part. So U is 4x squared plus 3. And then you're going to take the derivative of that. And so the derivative of U we're going to call du. And the derivative of 4x squared plus 3 would be 8x dx. And what I'm really doing is I'm separating the variables of differentiation. Okay, kind of like separation of variables for integration, but this time for derivatives. Okay, so if that's my U-substitution, what I want to have happen is I want to be able to rewrite this integral and not have a single x left behind. I want all those x's in terms of u. Well, let's see. The 4x squared plus 3 to the 9th, 4x squared plus 3 can get rewritten as u. So this is going to be u to the 9th. And then I still have a 6x dx. Okay, but down here I have an 8x dx. I didn't want 8x dx. I wanted 6. That's fine. Multiply both sides by 6/8. So 6/8 du equals 6x dx. So now 6x dx gets replaced by 6/8 du. So I really have the integral of 3/4 u to the 9th du. And that's a lot smaller. I can take that antiderivative just using a backwards power rule. So I'm going to add 1 to the power, divide by the new power, so divide by 10, which is going to make that 3/40, plus c. But if I started with x's, I really should end with x's, so I'm going to rewrite that as 3/40 4x squared plus 3 to the 10th plus c. I'm going to unsub my u. So the antiderivative of 6x times 4x squared plus 3 to the 9th is 3/40 of 4x squared plus 3 to the 10th plus c. The nice thing about antidifferentiation is while there are no rules, it's always checkable. If this is the antiderivative, the one thing that has to happen is the derivative of this boxed-in thing has to end up equaling my integrand. So let's give it a shot. d dx of 3/40 times 4x squared plus 3 to the 10th is going to be, let's see, the 3/40 will stay. Bring down the power. Reduce it by 1. Multiply by the derivative of the inside. Well, 10 goes into 44 times, and 3/4 of 8 is 6. So I'd have 6 times 4x squared plus 3 to the 9th times x. Yeah, that's 6x, 4x squared plus 3 to the 9th. Ta-da! There you go. Let's come down here and do another one. Example number 2. E to the x times sine e to the x dx. Well, when I do a u-sub, the thing in the parentheses is often going to be your u. So u is going to be e to the x. Du is the derivative of e to the x, and that's e to the x dx. And so now I'm going to write my original integral in terms of u. Okay, so in this one, I'm going to make a mistake right now. So if you want to wait and only write it down without the mistake, don't write right away. So I come up here and I say, okay, e to the x, that's u. Sine e to the x, that'd be sine u. And dx, that'd be du. I made a big mistake. I did it on purpose, but I made a mistake on purpose. When you are substituting, you want to make sure that everything's going in its place here. Yes, u is e to the x, so I could put a u here. Yes, u is e to the x, I could put a u here. The problem is when I wrote this du, du represents e to the x dx. This du here is representing too much stuff, okay? What we really need to do for this one is realize that since e to the x dx is du, that means e to the x dx is du, and sine e to the x is just sine u. This becomes sine u du. No extra u in the front, okay? So u is e to the x, du is e to the x dx, so I have the integral of sine u du. The antiderivative of sine u would be negative cosine u plus c, and then I'm going to unsub my u sub. Negative cosine e to the x plus c. And then if I want to check, the derivative of negative cosine would be positive sine e to the x times the derivative of e to the x. And hey, that's what we had. Okay. Now, before I move on, I want to give you one other heads up here. The techniques of integration that you have learned so far are technically 3. Technique number 1, backwards power rule or ln rule. Technique number 2, u-subs. But technique number 3, that's also a great technique for antidifferentiation, is guess. Now, I don't just mean blindly guess. I mean use an educated guess. So if I come up here and I were to do this one again, let me do it in some like garish pink here. If I needed to know the integral of 6x times 4x squared plus 3 to the 9th dx, instead of using a u-sub, I could say, wait a second. If I have 4x squared plus 3 to the 9th, it stands to reason that I probably, in my antiderivative, had 4x squared plus 3 to the 10th. Because if I have something raised to a power like that, it's probably a chain rule that's occurred. So guessing is a legitimate antidifferentiation technique. So 4x squared plus 3 to the 9th used to be 4x squared plus 3 to the 10th. Then we check and fix anything that's missing. So I say, well, if I'm right, if this is the antiderivative, then the derivative of that would be 10 times 4x squared plus 3 to the ninth times 8x, which is 80x times 4x squared plus 3 to the ninth. Well, I don't want 80x, I want 6x. So maybe I just put a 6/80ths in front, which would put a 6/80ths in front of here when I take the derivative, because a coefficient is just going to come along. My 80s cancel. 6x times 4x squared plus 3 to the ninth. So the antiderivative is 6/80ths, 4x squared plus 3 to the 10th. 6/80ths is the same as 3/40ths. I can do something similar down here and say, well, if I wanted the integral of e to the x times sine e to the x dx, if I have a sine function there, I know the antiderivative had to involve a cosine, and in fact a negative cosine, because the derivative of cosine should be negative sine. So that antiderivative is negative cosine. The angle never changes when I take derivatives or antiderivatives. So I'm going to guess and say, I think my antiderivative is negative cosine e to the x. Well, let's see what happens. The derivative of negative cosine e to the x would be positive sine e to the x times the derivative of the inside. And that's exactly what we had. So I can find my antiderivative in my head, too. Now, I've been doing calculus for a long time, decades, literally. So I can do this in my head maybe faster than you can. But if you're pretty good with your mental math and you have a little bit of calculus intuition, this stuff works. All right, let's come over here and talk about, what about definite integrals? So when you have a definite integral, when you switch from dx to du, you need to use what are called U-bounds. You need to switch the limits of integration, and that's what we're going to talk about right now. So I have 5x times x squared plus 1 square rooted. So if I do a U-substitution, I'm going to let u be the thing on the inside of the parentheses, which is going to make my du 2x dx, because the derivative of x squared is 2x. Yeah, you know what, though? I need 5x dx, so I'm going to multiply both sides by 5 halves. So 5 halves du equals 5x dx, just like I want. So this is going to become the square root of u, which is u to the 1/2. Sorry about my jumpy screen. And then 5x dx gets replaced with 5 halves du. Now, what about those limits of integration? I cannot bring them with me, because your limits of integration belong to the dummy variable. That's a 0 and a 3 on a dx. That means that those are x values. Now I have a u, so I need U-bounds here. And getting U-bounds is actually really easy. All you do is you plug your x bounds into the U-sub. So if I plug 3 in for x, 3 squared plus 1 is 10. And if I plug 0 in for x, I get 1. So when you have a definite integral that you then use for a U-substitution, you don't just bring the limits of integration along, you change them into U-bounds. Then I'm going to come over here, and I have 5 halves u to the 1/2 du from 1 to 10. I'm going to add 1 to the power, divide by the new power, put that 5 halves back. This is a definite integral. I don't need the plus c. And in fact, I don't even need to go back to x. Because it's a definite integral, it says take the antiderivative. I did that. Plug in the bounds. Okay. And subtract. Well, okay, I guess I'll do that then. So this is going to be 5/3, 10 to the 3 halves, minus 5/3, 1 to the 3 halves. So this is just going to be really 5/3, 10 to the 3 halves, which is an ugly number, so I'm just going to leave it like that, minus 5/3. And that's my answer. Okay? So when you have a definite integral, you're going to want to use U-bounds. Okay? And the nice thing about that is, when you have a definite integral, when you have something like this, the goal isn't to find the antiderivative. The goal is to evaluate the integral. Nobody actually cares what the antiderivative is because it's just a tool to get to the answer for the definite integral. On the indefinite integral, the goal of something without limits of integration is to find an antiderivative. I want to know what's the antiderivative of 6x times 4x squared plus 3 to the ninth, and I found it. I wanted to know what's the antiderivative of e to the x sine e to the x, and I found it. When you have a definite integral, I don't really care what the antiderivative is. I just want the answer. Okay? So when you have a definite integral, you're going to do a U-sub, substitute in some U-bounds, and that's how you will get your answer. Okay? Let's do another one, and then we'll stop with 4 because this video I know is already a little bit longer than I normally like to go. Integral from 1 to 2 of dt over t plus 1 cubed. All right, well, what am I going to do here? I don't really like that dt on top, so I'm going to rewrite this as 1 over t plus 1 cubed dt. And the thing is, when you're integrating, fractions aren't always the best. So if you don't notice another way to take an antiderivative, make your fraction a negative exponent. All right, so that's a whole different way of thinking about the integral of dt over t plus 1 cubed. So now I'm looking at this and I'm saying, well, I don't have a product this time, but I do technically have a quotient that I can't get rid of. So I'm going to let u here be t plus 1. Du would be the derivative of t, which is 1 dt. So then if I wrote this using u's, I would have u to the negative 3 dt gets replaced with du. Then I'm going to do U-bounds. So if I plug 1 in for t, I get 2. Plug 2 in for t, I get 3. Then I'm going to take the antiderivative. I'm going to add 1 to the power, divide by the new power. Evaluate that from 2 to 3. So I have negative 1/2 of 3 to the negative 2 plus 1/2 of 2 to the negative 2. I'm writing a plus because it's minus a negative. So this is going to be negative 1/18 plus 1/8. And you know what? I'm just going to leave it like that because I'm lazy. And that's good enough. Okay, so there's your answer. Now, if you look at the header here, it said U-subs and a trick for linear expressions. I'm going to do this one another way using a kind of a trick. If you have a linear, and only if you have a linear expression, like t plus 1 to the negative 3t dt, you can do a backwards chain rule. And what I mean by that is you can say, well, if I have t plus 1 to the negative 3, I'm going to do like what I did on the other page. The antiderivative is going to be add 1 to the power, divide by the new power, and you divide by the derivative of the inside. The derivative of t plus 1 is 1, so technically I would divide by 1. Now, obviously, that's silly. Dividing by 1 doesn't do anything, okay? But I can find my antiderivative, if it's linear, by adding 1 to the power, dividing by the new power, and dividing by the derivative of the inside. And then evaluating from 1 to 2. So I have negative 1/2 of 2 plus 1 to the negative 2, that's 3, minus a negative 1/2, 1 plus 1 to the negative 2. That should look familiar because it's the exact same thing I got before. All right. I want to stop here so this doesn't get too long. You're probably just going to watch the second half pretty soon after this first one, but I think it's a good time to close. And I will close with the best joke about U-substitutions there is. I don't like my current partner. Can I do a U-substitution? One of the best pickup lines ever, although not really. Terribly corny, but I don't like my current partner. Can I do a U-substitution? Enjoy the rest of your day, and we will talk again soon.